I am going live. Yeah, Prahladh, you can start.
Started the third lecture on interactive proofs. So, sort of give a proof we wanted to. The goal of doing this, we wanted to give an alternate. Recap. Let's recap from last time. We had to show that we had defined hash set D as follows. You're given a formula phi, say in 3CNF form. Phi is in 3CNF form. And we say the number of satisfying assignments of phi is equal to Q. This is what we want to prove. And we want to prove hash set D is in IP. Now let's just quickly, just for our own sake, recall what does it mean to say something is an IP. We have to design a protocol. So we have to do, what does it mean? What does it mean to say L is an IP? So we have to design a protocol. Designing a protocol just means designing the verifier's actions. Just like even in an NP world, if you want to show some languages in NP, we only talk about how the verifier is going to behave, not how the prover is going to behave. So we're going to talk about how both of them have this. We're going to design a protocol, a sequence of steps, which is basically we have to tell what is the next message function over here. So at each step, the verifier tosses random coins and going to ask a question to the prover based on this random coins. So Q in general, in the ith step, Qi is going to be a function of the input of the random coins it's going to toss up to the ith step, and the entire sequence of answers it has seen up to the I-1 step. So the prover is returning answers. Okay, my Q's and A's are very indistinguishable, depends on the tail. So the verifier is just this. So we had to design this sort of protocol from the verifier, and it should have the following property. One, the first property is efficiency. So this is the next message function. Should be computable in poly time. Poly time in the input description, not in poly time of its inputs. Poly time of the original input X. 2, then completeness. This is like NP. For all X in the language, we want to say now there exists a prover P such that when this verifier talks with this prover and tosses whatever random coins it tosses, it accepts this should be greater than or equal to 2/3. And this is like there exists a proof. So here there exists a prover protocol that starts this. The soundness is the other statement. Soundness states that if X is not in the language, then for all provers, no matter which prover you give, tell me which prover strategy you provide, the verifier can't be convinced with too high a probability. Okay. So these are what were the main things that we needed to show. We needed to come up with a verifier protocol that had these features. Are people with me on this? And we gave one protocol for the permanent. Now we wanted to give, which already showed that sharp P can be done in interactive proofs, can be done with an IP protocol. We are now going to reprove the same statement, but we'll show that number sat can also be done. Of course, this can be shown by just reducing number sat to permanent and then doing the previous protocol, but we want to give a first principle protocol for number sat. And we gave a protocol last time, which was not sound. It was similar to the non-sound protocol that we gave for permanent. Then we worked that we actually just can't work with SAT. We needed to do this thing called arithmetization. So it's a sort of a, and what is arithmetization in general? It refers to a low degree polynomial representation of a function, of a Boolean function. Need not be Boolean, but we will be working with Boolean functions. So in particular, what are we going to do? We give me phi, which is a 3CNF formula. We are going to convert it to P phi, which is a polynomial. We did this last time. I'm just recalling this one, but it will have the features that for all Boolean inputs. So the 3CNF formula is defined only on Boolean inputs. It's only defined when x1, x2, xn are 0 and when the xi's are 0, 1. But because P phi is now a polynomial, the polynomial P phi is on the other hand, because it's a polynomial, it's defined when you could plug in any field element to x1 to xn. But what I want to say, despite that, as long as you restrict to the domain to be just the Boolean 0, 1 values, these two, the P phi and P should be the same. In other words, for all B1, B2, Bn in 0, 1 to the n, if you look at this, phi of B1, B2, Bn should be equal to P phi of B1, B2, Bn. Notice for say an alpha 1, alpha 2, alpha n, which is in f to the n minus 0, 1 to the n, phi of alpha 1 to alpha n is not defined at all. However, P phi of alpha 1, alpha 2, alpha n is something we can compute. If we have the polynomial, I can plug in alpha 1 to alpha n and find out is well defined. Okay, and how did we define? So definition of P phi. This is where we did it inductively as follows. The base case is if phi was a constant. Let's just recall what we did at the very end of last lecture. If phi was a constant 0 or 1, then P phi is the same constant. So constants we know how to do. Next was variables. So if phi was the variable, say xi, then P phi is also just set it to be the linear, just the constant, the linear polynomial xi. Then the next was negations. If phi was equal to not psi, then it's easy to set P phi. We will set it to be 1 minus P psi. So inductively, I assume P psi I have computed. So from that, I can compute P phi by just stating P phi to be 1 minus P psi. So on Boolean values, this will match. Notice for if psi does not output a Boolean value, 1 minus P psi somehow will output something else. I do not know what it does, but it's a well-defined quantity. That's this one. Then let's define forget this. This is conjunctions, no? And or conjunctions. So suppose phi is psi1 and psi2. Then we saw that p phi, we just defined it to be p psi1 times p psi2. Construct the polynomial corresponding to psi1, multiply it with the polynomial corresponding to p psi2. For Boolean values, this is going to compute the AND function. For non-Boolean values, I have no clue what it does, but it does something. And of course, I don't have to say disjunctions. We could use De Morgan's rules, but let me just write it down anyway. So disjunction. So phi is same psi1 or psi2. So this is the same as not psi1 and not psi2. So we just apply the previous thing to say p phi is 1 minus p psi1 into 1 minus p psi2. Okay. So is the definition of arithmetization clear? This is how I'm going to arithmetize this one. Now, if phi were a 3CNF formula, I want to now understand if I apply this process, 3CNF formula, say with m clauses. That is, phi is itself with the form C1 and C2 and Cm, where each I its Ci is of the form xi1 or xi2 or say something of this form. We want to look at what does p phi look like. So p phi, in fact, Kritika, what I want to ask is what does degree p phi? So first, let's look at what is if I have a clause, say I have a clause x1 or x2 or x3 complement. What does degree of PC look like? How much will this be?
3.
3. Even if they are negated variables. Negation does not increase the degree. Ors and ands will just be the product of the degrees. Will cause a product. It might collapse. This product might further collapse, but this is a upper bound on it. Therefore, degree of p phi itself is going to be at most 3n. So it's a small degree polynomial. Small degree polynomial, 3n. Okay. So that is fine. And furthermore, by definition, by construction, we have our, I'm just reiterating this again and again, p phi and phi agree on Boolean values. Okay. Now let's say, what did we want to check? Want to give an IP protocol to do the following check. Check that D1 is in 0, 1, D2 is in 0, 1, all the way up to Bn is in 0, 1. This summation of phi of B1, B2, Bn is equal to K. We needed to check this. Now, because this quantity was the same as this one, because
you can replace the phi with the p.
So that's exactly what I'm going to do. I'm going to replace. So suffices to do this one, which here I'm not going to have phi p5. Okay. And we will do the arithmetization on some finite field. So we will actually be working with some finite field, some suitably large finite field. How is large? We will see, the proof will eventually. Suitably large finite field. Notice arithmetization is true over any field. I could have done this process over any field. We'll work with some finite field, and that size of the finite field will just come as a consequence of the arithmetization. Just for notation, I'm going to define the following quantity. I'm going to define this thing called Si of alpha 1, alpha 2, alpha I to be a function Si. This is going to be the same summation, except that this one is going to have the first I terms of the summation are going to be dropped off, and instead of those some things, I'm going to put in alpha 1, alpha 2, alpha n. So this is going to be the summation over bi plus 1 in 0, 1. I'm defining this. Yes, I alpha 1, alpha 2, alpha I. I'm defining this to be this quantity. bi plus 2, 0, 1, all the way up to bn 0, 1 of p phi. The first I, guys, I'm going to put alpha 1, alpha 2, alpha I. The next I'm going to put bi plus 1 all the way up to p. Okay. And so this star is just reduces to string. Star is equivalent to S0 equals K. Okay. So what we'll actually prove, we will show, we will give an IP protocol for not just S0, for any Si alpha 1 to alpha I equals some context, or what should I call it, Ki. For any I from 1 to n and alpha 1, alpha 2, alpha I in F and Ki. We will prove this in general for any such this one. And one setting of things will be the one which we care about will be a specific setting of the type. Okay? People with me so far?
So Prahladh, roughly the size of the field must be, eventually it should be larger than 2 power n or something? I mean,
Yeah, some sense the size of the field has to be, so because you want to get K exactly, it has to be larger than 2 power n. Otherwise, you'll have to run it on several prime fields with large enough and do Chinese remainder theorem.
but is there any particular reason that we won't work with, say, the rationals or something? I mean, why does it have to be is there a reason for a finite field?
You can work.
I guess everything over characteristic 0 would always do, right? Like previous.
No. The only issue is with regard to these computations, I guess.
So you have to pick the rationals from these grids.
Yeah, that's okay. But I presume, I mean, it's probably more cumbersome to work with it, but
yeah, it should.
yeah.
You'll have to just, the only problem is there, you will have to show the bit complexity doesn't shoot up and stuff.
Yeah. So maybe this is cleaner. Okay.
Also, like previously, in the previous protocols, also when permanent was there, fields of characteristic 0 would also have done the job.
The permanent also, did that have worked?
In the permanent thing, fields of characteristic 0 would also have done the job.
I think the proof would have worked. Yeah.
Yeah.
So I'll state it for S equals K, but then we will see more in general. I'll say so this is what S0 equals K. This is what the prover wants to convince the verifier. So this is something the verifier has, and the prover. They both have this common statement. In general, it will not be S0 equals K. It will be Si alpha 1, alpha 2, alpha I is equal to Ki. That will be the statement. And the prover wants to convince this guy, this is the statement. Now, let's look at S1, X1. S1, X1. So what do we, if you, let's write this. S0 of something, by definition, is just S1 of 0 plus S1 of 1. In general, this is true for anything. Si of alpha 1, alpha 2, alpha I. The way I have defined it is exactly Si plus 1 of alpha 1, alpha 2, alpha I, 0 plus Si plus 1, alpha 1, alpha 2, alpha I, 1. The way I have defined Si, that's, you should see that is clearly the case. So what the prover will do is, he's now going to give,
it will compute P and then give it back to the verifier.
What is P? What is P? So the prover will compute, the prover computes S1 of X, X1. It's going to compute this, so it's going to compute this polynomial, S1 of X1. Free variable, and just send this polynomial across to the verifier. The verifier checks if, what is the verifier going to check? He's going to check that K is equal to P, let's call this P1, P1 0 plus P1 1. So he knows that if P were correct, then K is correct. Just check. But now he needs to check that P is correct. So now he's going to pick a random R1 from the field and send that across. And what is he going to say? He's going to say, convince to me that S1 of R1 is actually P1 of R1. When he sends this R1, what he's actually saying is, what you should have actually sent me is S1 of X1. You possibly didn't send me that. You sent me P1 of X1. I do not know what is it. But assuming you have sent it to me, I checked it. Now I need to check that what you sent, P1 of X1, is the right guy. So at a random point, convince to me these two guys are the same. And I haven't yet told you the random point before disclosing P of X1. Now I told you the random point, and now the random point convinced me this one. So the protocol will just go the same way. So now it's reduced to a smaller setting of it. Now the verifier, he's now, as before, we know that S1 of R1 is the same as S2 of R1, comma 0 plus S2 of R1, comma 1.
Could you just go back to how you defined S1? Yeah, okay.
S1 will just have one variable, and all the remaining variables, it will be summed over 0, 1. So S1 R1 is S2 R1 0. So what the prover will now give me, he will now give me the polynomial P2 X2, which is S1 R1, comma X2, and send this polynomial across, P2 of X2. The verifier will do the same check now. He'll just check that S1 of R1, sorry, he will check that
P1 of R1.
P1, what's that? I don't know what that is. P1 of R1 is equal to P2 of 0 plus P2 of 1. And then he will now pick an R2 randomly from F and send R2 across. But what is he actually asking? He is now going to ask the prover to convince me that S2 of, rather, he's going to ask the prover to convince me that P2, S2 of R1, R2 is equal to P2 of R2. And this is inductively, this will continue for n rounds. And the last round, he's not going to ask the question. Last round, when the last round, what is going to happen when he picks Rn equals F? He needs to now check, but he needs to now compute S of R1, R2, Rn. But at this point, he can now, this is just P phi of R1, R2, Rn. And this, he can actually just plug it in and compute it. So the last round, the verifier does not, at the last round, verifier does not employ the prover. Now it's almost identical to the way we did the permanent setting.
So one thing, like, could you go a bit up?
Yeah.
The S1 of X1, how much time does it take to calculate that? Because like there are 2 raised to.
Yeah, for the prover, it's going to take a long time to calculate it. The
Yes.
prover the exponential time to calculate it.
Yeah.
But once calculated, it's a univariate polynomial of degree. So that's where let's come to efficiency. The prover takes a long time to calculate S1 of X1. But once it's calculated, that is a univariate polynomial of how much degree? The degree is at most 3m. Notice that once P phi is degree sum, all the degrees of all the polynomials that you compute as S1 of X1, how large can the degree be? It can at most be 3m. So all you're just summing over things. You're summing over a polynomial. It's never going. The degrees. These are summations of the same polynomial. It's never, the degree is never going to increase. So P is a 3m degree polynomial. Therefore, even though the prover took exponential time to calculate it, to send this across, he has to just send 3m coefficients, 3m field elements.
So in the efficiency, prover's efficiency isn't taken into picture.
No. So just like NP, we never cared how much time it took to compute the proof.
Yeah.
To check the proof is what we cared for.
Yeah.
This is a point in which you have the ability to converse with a prover whom you possibly don't trust. This one, but the prover can do whatever they want to do, but you have to be efficient from your end. The prover, you don't put any constraints on the prover's end. So let's just see. So I want to claim efficiency. So each of the polynomials Pi is of degree at most 3m. Hence, all transcripts, everything are polynomial. Efficiency we do have. What about completeness? I want to claim in this case also, if actually the number set is equal to k, there is an honest prover which can compute everything correctly and give answers, and it will be, and everything will go, every check will go perfectly, and the verifier will answer it. So we do know there exists an honest prover. There is an honest prover. P such that, so I'm assuming that phi k is in sat B, number sat B. Then such that probability over the various random points R1, R2, Rn. This is R. When this V talks with this prover on phi k and this random string R, it accepts is actually probability 1. Let's look at soundness. Okay. So here now we are working with the phi k, which is not in number set T. So the number of satisfying assignment is not k. And now let P star be any prover, not necessarily the honest prover. What we need to look at, we need to compute this quantity. Okay. Now let's just stare at this proof. Let's stare at this proof and see what happens. Now, if the prover actually sends the right P1x1, then he's going to be caught. Then that P1x1 can't satisfy this one. So if he wants to cheat, if he wants to increase the successful probability, he has to send the wrong P1x1. If he sends the right P1x1, the right P1x1 does not satisfy this condition. So he has to send at least something which is not, if he wants to do something, if he wants to continue the protocol, either he sends the wrong thing and you verifier rejects right away here and the rejection probability is 1. Or he sends some polynomial which is some degree 3m polynomial which is not the right polynomial. But that right,
but it evaluates to the correct value on 0 and 1.
It's not the correct value. It evaluates to two numbers P0 and P1 such that their sum is equal to k. There is no correct value over here. There is no correct value. It gives rise to two numbers such that P0, he gives me some polynomial P1 so that P10 plus P11 is equal to k. So this check goes through. But the point is, it's unclear whether this guy is actually this polynomial. But if it is not this polynomial at a random location, it won't be this polynomial. Therefore, the probability that the verifier picks a point such that it actually happens to be a point at which it accepts, it happens with very low probability. Schwarzschild will tell you that this quantity in the first round will be at least 1 minus the degree of 1 minus D is D over the size of the field, where D is the max degree of all the polynomials and Q is the size of field. It's at least, this is just the first step. First step, the acceptance probability is at least so much. But then once again, now you've gone into a step, the second step, it's the same thing. And so on goes on for n steps. The probability of acceptance is at least this one, at least is. It could be all the way 1, 2. That is, if the
would go down, right?
What?
The degree of the polynomial would
decrease. Yeah. So that's only acts in your favor.
Yeah.
That acts in your favor. It's at least 1 minus d over q. It could be even larger than that, is what I'm saying. Therefore, this is 1 minus d over q to the power n, which is at least 1 minus nd over q. So if we choose this is at least say what do I want to say? I want to say it's greater than 0.99.
Q as 6n square or something.
Q to be larger than
3n square.
100 nd, and d itself is 100 n 3m. So if you choose this to be 300 mn, you'll get this. But of course, you needed the proof to be even larger because you needed the number k should not have dropped down. So you choose the proof that the field size to be like exponentially large in n, larger than 2 to the n, and you would be down.
I think a better thing is probably to do Chinese remainder, right? Because it's not even clear how you will find the prime that large.
Yeah, so just do Chinese the theorem. Yeah.
Okay,
So,
or you basically ask the prover to provide the prime.
huh? Yeah, you ask the
You
prover.
ask the prover to provide the prime, you just do some check on the side.
Yes, yes, yes.
So Prahladh, one minor thing. So here you are using the fact that the success probability in every round is independent, right? Because
Yeah.
there is a...
Yeah, so because
Okay.
there's an independent random coins you're tossing at every step. Random coins across the rounds, there's a fresh random coins is being tossed. Therefore, success probability in each step is independent of the success, what has happened so far. And that's why I'm able to, what Ramprasad is saying, that's why I'm able to multiply these quantities. These were independent things that were happening. I could have also done the union bound and done it, which is exactly what I'm doing eventually over here. It is each time the rejection probability, the failure probability is d over q. There can be at most n such things, therefore it's n dot. Eventually I'm doing that. So I could have done it the other way too. Even if the coins were not independent, this would have worked. Okay.
So till now, all examples we considered had like perfect completeness, right? Like,
Yes, yes, yes.
could you just give some other where it is at least 2 by 3 or like, because that case isn't quite clear. Like, when would a factor of 2 by 3 come in the case when x belongs to 1?
So, but the
You
point
can
is,
always boost it. You can always say that you can boost it to 1, but still.
no, boost will only push it close to 1. There's a way in which you can actually make it 1 perfectly. That's not easy to see, and that's when you're going to be in the 4th problem set. How to make it exactly.
But then could you just then this 2 by 3 example somewhere?
What's the 2 by 3?
So a stupid 2 by 3 example is to just take something in BPP already.
Yeah, but that doesn't involve the prover at all. That doesn't involve the prover at all. So we will see an example. We will see in the next lecture, we will actually see a protocol in which in the completeness case, it will not be 1. It will be less than 1. It will, so we will see a protocol, but I don't want to talk about what the protocol is right now because this is this Goldwasser-Sipser protocol. The Goldwasser-Sipser protocol don't have completeness 1. Okay. So what have we done so far? So let's just summarize what we have done so far. We gave 2 proofs of the fact P to the sharp P is an IP. One via permanent, one via sharp sat. And then we also saw this is in P space. IP is in P space. Last. Now, what we next want to check is which of the two, is this closer to this guy or is it closer to this guy? And the next we'll slightly modify the theorem which we saw just now to show that actually IP goes all the way to it hits the ceiling. IP is equal to P space. This is a theorem due to learned Fortnum, Karloff, Nissan, and Shamir. Basically, the way we will prove it is that is TQBF is in IP. That's what we need to show. Okay. Questions so far? I mean, what we're going to do is, and the way we are going to show TQBF is an IP is exactly, we're going to take the proof for number set D, which we showed so far, modify it so that it can handle TQBF also. Okay.
How just define TQBF? I don't quite recollect how.
Yeah. What is TQ? Let's just recall this. What is TQBF? Let's go to the proof of this guy. So an instance psi is an instance of TQBF. An instance, how does an instance psi look like? It looks like there exists x1 for all x2, there exists x3 for all x. These need not be alternating. There could be a sequence of x's, x's. Possibly there exists x4. And you have phi of x1, x2, xn. So where this is a 3CNF formula. And you want to check that psi is, no, so notice we have quantified all the variables, therefore psi is either true or false. And the question is, TQBF is exactly the set of those quantified Boolean formula which are true. TQBF is true quantified Boolean formula. Okay. And we're going to use the same idea. We're just going to arithmetize the thing. Previously, we arithmetized phi. Now we're going to arithmetize even psi. Phi was just the 3CNF part. We will arithmetize the whole thing. So basically, what we're going to do is we had this part. The x is xn. Phi of x1, xn. We knew how to arithmetize this guy. To get p phi of x1, x2, xn. Now what we'll do is we'll arithmetize. Now we'll arithmetize this part alone. We'll just take this guy. This is a variable. This is a formula that depends only on x1 to xn minus 1. That guy will arithmetize to get a formula. We'll arithmetize each one of them, and we'll show. Basically, we're going to extend the rules of arithmetization previously, which held good only for constants, variables, negations, conjunctions, disjunctions. That's how we got it. We'll extend the rules of arithmetization even for alls and their exists. So extend arithmetization to quantified, but even partially quantified. Partially quantified Boolean form. So once again, how am I going to do this? Once again, by induction. So let's look at psi. So the baby case over here is psi has no quantifiers.
So just one thing, in the above arithmetization process, suppose the x1 was say b1, such that this phi worked out, that phi of b1 comma for all x2 comma b3.
Yeah.
This p of phi is also satisfying that, right? It is already arithmetized the whole quantified thing, right? Like, since because phi of b1.
So let's just the thing will come right in the next step. When I do the next step, we'll do. So suppose psi, I'm working not just fully quantified formula, I'm even working with partially quantified formula, in which not all the variables have been quantified. So phi has some variables, not all the variables have quantifiers sitting up front, in front of it. So suppose there are no quantifiers, then we know how to arithmetize it. This is exactly what we did previously. Then psi is a 3CNF formula, then p psi is obtained as before. And notice p psi, but now the next case is psi is actually, suppose it is for all x phi x. I can't put p phi of x. P phi of x, something that depends on x. Psi does not depend on x. Psi is a thing that does not depend on x. It's quantified. It's because of the for all, the dependence on x has gone out. So p of psi should also be a formula that does not depend on x at all. Psi doesn't depend on x. So p of psi will also be something that doesn't depend on x.
P phi of 0 and P phi of 1.
Yeah. So basically, what we'll do is the definition should be clear. Exactly what this should just be p phi of 0 times p phi of 1. I just do that. More generally, so if something is causing you confusion, so it could be that this is actually more, let me say, take a slightly general setups in which I have for all x, phi of x, y, z. I have this intermediate step. And this happens to be my psi of yz. Psi of yz is for all x, phi of y. So the only free variables now are y and z. So p of phi of yz will be p of psi of yz will be p of phi of 0 yz into p of phi of 1 of yz. That's what I mean by the above. Okay. So does this answer your question, Satyajit? So p of phi is the same as p of psi. Variables are disappearing from the picture. Psi is depending on lesser and lesser. As you quantify, those variables are disappearing. So you have to come up with an arithmetization which depends on fewer variables. So once all the quantifiers are knocked out, what you get is now a thing which has no variable. So all you're getting is actually a constant. And what you want to know is that constant 0 or is that constant 1? That's what you want to ask. TQBF is checking that finally when you open this out, by the way, so because we did this, let's do this. Let me just finish off the thing. When psi is, there exists x, phi of x. So what will this be again?
It's 1 minus thing. 1 minus 1 minus p of psi into.
It's the same thing. This is going to be 1 minus p of phi at 0, 1 minus p of phi at 1. The other variables remain as this over here. Okay. And what is now? So let's look at the protocol. So we are given the input to the provers. This one is some psi, which is q1 x1, q2 x2, qn xn, phi of x1 to xn, where each qi, where the qi's belong to are either the exist quantifier or the for all quantifier. And what do we want to check? Finally, p phi. We want to compute p phi. When you do p phi, all the variables are knocked out. P phi is now a constant. What we want to check is p phi is 1. We want to check this.
In chart set, we talked about the number of assignments. Here we talked about whether the assignment is evaluating to 1 or 2.
Yeah, whether the formula is evaluating to 1 or 0. This is what we want to check. Okay. And the proof, I'm going to write a proof once again. So in general, what we will show is, so they both get p. They want to get p phi 1. This is what he wants to prove, the verifier and the prover. Now let's assume psi is of the form for all x1. So psi is something of the form. Psi looks like for all the first quantifier for all x something phi of x1. This is what psi was. So p1 of psi. So p of psi, we know p of psi is exactly p of phi 0 times p of phi 1. What we'd expect the prover to send us is actually p1 of x1, which is p of phi of x1. Send me this across. Send me this p1 x1 across. And what will the verifier? The verifier checks that 1 is in fact equal to p1 0 times p1 1. He wants to check that p1 has been evaluated correctly. So now he does the same thing. He picks an R1 completely at random from F and sends R1 across. So now the prover needs to prove that P psi, sorry, what does he need to prove? He needs to prove P phi of R1 is equal to P1 R1. This is the same thing. You now peel one more quantifier, and you keep doing this.
Just one thing, like below the prover, you have written P1 x1 equal to P phi of x1, right? It should be, you have written P phi 1.
What?
Below P1 x1 is equal to P phi of x1, I guess. That should be, you have written P phi 1 of x1.
Where is?
Just below the prover thing.
Yeah, there is just yeah. P5, yeah. And we'll keep doing this. We will shave off each time. He's going to get the polynomial for the next guy and keep doing this. So let's just ask us a couple of things. This one. So once again, if you see, completeness will be it should be clear that the completeness is actually true. If the prover behaves honestly, everything will go through. And identical to our proof previously, soundness will also go through. Every single step, soundness also goes through. What I want to know.
The bound will also be the same, right?
Huh?
The bound will also be the same, right?
The bound will also be the same. It's 1 minus d by q the power n. Yeah. Oh, the proof is the same. Now let's come to efficiency. And what I want to ask is all the polynomials that I send, are all of them small degree? Previously, we knew that the P of phi was 3m, and all the intermediate form, none of the intermediate formulas ever grew in degree because they were just summations of these formula. Question is, so degree of the, so if psi is equal to a whole bunch of quantifiers and phi at the end, then certainly we know degree of P psi is less than or equal to 3m. This is by previous constructions. But let's take even if you put one extra quantifier over P phi.
It's always going to add up to the degree rather than multiplying, right? Anyway, so
No. So here we are multiplying so what are we doing over here? The way we did
multiplying the polynomials, but the degrees get added up, right?
Degree gets added up. So the degree can double at every step.
Yeah.
After m steps, the degree could have just blown up to 2 power m. The degree is no longer, the degree could double each step because of this process. The degree adds up, I agree. So the degree was 3m. The first quantifier, now I'm going the quantifiers from the rightmost side. The rightmost quantifier, when you do it, the polynomial becomes possibly 6m degree. Then the next guy becomes 12m degree. Then the next guy becomes 24m. And so on, it can become, so the degree of the polynomial. So each quantifier, each application of quantifier from the right doubles the degree. So the final polynomial can have degree as large as 2 power n into 3 power 3m. But this is prohibitively large because the prover can't send, he can of course send these coefficients, but the point is the verifier has no time to read these coefficients. So efficiency, we are in for a this one over here, efficiency is not working out. So this is, we are in a one over here. We need to fix the protocol, we need to get back the degrees small. If the degrees were controlled, then we have worked. The question is, we need to look. This is a very rough estimate of the degree. We just said each time the degrees could potentially blow up by a factor of 2. We want to actually look, does it really blow up by a factor of 2? We need to look at this and see if we can get a better. Can the prover give me low degree polynomials each time? Only polynomial degree polynomials, not very large polynomials, not polynomials with very large degree, with exponential degree. Polynomials which have only polynomial degree. If that was the case all the time, then the protocol will be efficient. Otherwise, it's not efficient. Is the issue clear over here? Why we are running into problems? So now we need to. So what we're going to do
something with multivariate polynomials and get down the degree or no?
Yeah, so we are going to do something. So we want to. This one is we need to. The idea is going to be to modify the protocol. Modify the protocol so that the degrees do not blow up. And how do we do this? What do we want? So now let's go back to our question. What do we want of the arithmetization? The arithmetization, we want it to be some polynomial such that on the Boolean values, these two match. On the Boolean, that's all we cared of the arithmetization. It could be anything. It's fine. So notice what do we want? Arithmetization. What we want of this is just a polynomial such that on Boolean values, matches with original function. Now, suppose I gave you a large degree polynomial and I cared about its value only at 2 places. I gave you a large degree. Let's work with just univariate polynomial. It's a very large degree. I cared about its value only at 2 places. Can you come up with an equivalent polynomial from this which has much lower degree?
You can do interpolation of some sorts, right?
Yeah, you can. All you care is only the polynomial at these 2 points, say alpha and beta. So I give you a p which is a very large degree. I compute p of alpha, I compute p of beta, and then I just construct a linear polynomial that goes at these 2 places. You are done. So all that we care. So what we'll do is, suppose that's exactly what we will do. So if you give me any time the polynomial goes of large degree, we will sort of interpolate it and get it back to low degree by doing this linear interpolation. So more precisely, what do I mean? So let P be a univariate polynomial of possibly large degree. Now I'll define Q of X to be this polynomial, X into P of 0 plus, X into P of 1 plus 1 minus X into P of 0. So suppose I define this Q of X this way. Let's ask a couple of features. What's the degree of Q in terms of X?
1.
It's just 1. What is Q0?
P0.
P0.
And Q1 is P1.
Q1 is P1. So Q is a low degree. It's a degree 1 polynomial that has the same feature as P. In a particular on Boolean values, this was low. It was degree 1 because it was 2. We cared about it only at 2 places. If we cared about it at 3 places, it would have been degree 2. You could do a linear interpolation at 3 places and do. So this is what we are going to do. Each time the degree goes up a little large, we are going to do this process of what I'm going to call, this process is what I'm going to call linearization. So this
But
operator.
suppose like you have a high degree polynomial as well as you wanted to evaluate at a number of suppose the degree is like the degree is also high, but you want to evaluate it also at high number of points. That will also blow up the degree, right?
What?
So suppose you want to suppose you have a high degree polynomial and you want to evaluate it at a number of points. That will also blow up the degree, right? But
yeah, but with you see the way we'll do this is what I'll call the linearizing operator. Linearizing operator satisfies, so it is Lx of Px is Qx, is defined to be the Qx which I talked about. It takes a large degree polynomial and gets it's linearizing only in this variable x. P could have a larger degree in the other variables. I'm not doing anything about it. For this variable, because I care only about them. So for each variable, we'll apply a linearizing operator. We'll take the one variable, we'll apply the linearizing operator. So in that variable, the degree has become 1. Then we'll apply the linear operation on the other variable. Again, it will become 1. Because each variable is allowed only in 0, 1 values. So each variable will do this one after another, so that the degrees in each variable becomes 1. Of course, if the degree in each variable is 1, the total degree can be at most n.
yeah.
So each time we get a polynomial, if we do not know how large the degree is, we'll apply all the n linearizing operators on it, all possible linearizing operators, so that each of them will reduce. So each time you do one of these quantifiers, you blow up the degree, we'll just get back the degree back to small by applying the linearizing polynomials. So what we will do, so the input was once again psi, which looked like q1 x1, q2 x2, qn xn, and phi of x1, x2, xn. We already changed this to be going to so we made this p phi of x1 to xn. Then we applied what I call the p qn xn operator. That is going to take this, and this is what we did before without the linearization. That is, and then we further then p qn minus 1 xn minus 1. We sort of did this sequence all the way up to p q1 x1. These were the we took this thing when we did these sort of operations on them. This is how we arithmetized. But the problem with this was each of these guys double the degree, potentially double the degree. So we want to get the degree back to controllable features. So what we'll do is, whenever the degrees are too large, we want to get it back to this one. So what we'll do is we'll intersperse these guys with the linearizing operators. So what we'll do at this point itself, the degree in any variable could be quite large. It could be as large as 3m in a particular variable. We'll get it down to 1 in that variable. So what we will do is we'll take p phi x1, x2, xn. We'll apply the linearizing operator on xn minus 1 all the way to x1 on p phi. I do this. This has ensured that the individual degree in each variable has dropped down to 1. And then we will do pqn xn. This could have once again doubled the degree. But now once again we'll attack it with but the xn variable has disappeared now. You don't have to linearize. The xn variable has disappeared once you do this. Once you do this quantification, it no longer depends on the variable xn. That has gone out of the picture. So you need to only linearize with respect to the other variables, xn minus 1 and so on all the way up to lx1.
And then again you do pqn minus 1.
You do pqn minus 1.
Yeah.
Do on, so all the way up to pq1 x1. There you don't have to do anything further, because at that point every variable has dropped out. There is no degree left. So this is the guy which we will finally work with. The protocol will take this guy. So here all the guys are of controllable degree. When we need to show how to write a protocol for this. So at the end of this process, individual degree in each variable is less than or equal to 1. Hence, total degree is less than or equal to n. And how many such operations are we doing? How many polynomial operations are we doing of this, right?
N rounds, right?
So initially there are n rounds, then there is the first quantifier, then there are n minus 1 rounds, and then the second quantifier. Then there are n minus 2 and the third quantifier, and so long up to n minus n plus the nth quantifier. So that comes to something like order n squared. So now the protocol will not be a n round protocol, it will actually be an n square round protocol, because we'll have to eliminate each of these operators, each of LX1, PX1, each of them we'll try to eliminate. For eliminating each one, there will be one round of the protocol. Are people with me?
Yeah.
So I'm going to write this very generically as the following. You are given
The degree would be like n cube or n raised to 4, something like that, right?
No, the degree is going to be very small. The degree at this point is 3m.
Yeah.
This point onwards, the degree is only dropping. At this point, the degree becomes n. At this point, it becomes 2n again, and then drops. So the degree will always go between, it's a max of 3m and 2n. It's never going to go more than that after that.
Yeah, okay.
The degree now is, so let's write that also. Let's actually write degree of any intermediate polynomial is either less than 3m. 3m is the final guy, but after that was the initial guy. The initial guy you started off with 3m, but after that, after all the linearization operators, the degree dropped to n. And then once you apply the first quantifier, it went to 2n. But then it could drop. Once again, you apply all the linearization, it will come to n again. So at no point, all I'm claiming is it's going to be just a max of
at most 3m or 2n.
3m and 2n.
Yeah.
This is a polynomial thing. Therefore, now efficiency will be taken care of. But I do not know about this one. So now all I'm given p psi. P psi looks like what? It takes p phi. P phi, then it applies a bunch of operators. It applies either a for all x1 operator, or there exists xn minus 1 operator. So it basically, it looks like this. Let's write it this way. It looks like theta q1 x1, theta q2. And these xi's could be the same guy now. qm xm p phi, where each theta qi xi is one of them. It's either the linearizing operator linearizing with respect to xi. It's either the linearizing operator, or it is the existential operator, or it is the for all operator, universal operator. Okay, so you're taking a p phi and you're applying one of these at each step, and you want to shave them off one after another. Yeah. We want to do exactly the same protocol. We're going to do this. Now I want to say everything, all the issues in the previous step get fixed. Question is, do I want to do the proof? Is it one? Is it worth doing this proof? So this linearizing operator takes care of it. I'm going to skip the proof of this. You can check the proof of this. There's nothing more insightful in this proof than the sharp peak proof. You can show that everything is done. Look at Arora Barak for doing it. I don't want to waste 15-20 minutes. It's cumbersome doing this whole proof. That is, you can do it round by round, remove each of these operators one after a time. So we'll basically, I'll write down the claim that we will show. Show the following. So let G of x1 to xs be any such intermediate polynomial after shaving off polynomial on variables x1 to xs. The claim which we will be proving is the following. For all a1 up to as in f to the s and a c in f, there is a protocol, there is an IP protocol such that an efficient IP protocol that in case 1, in which GS of A1 up to AS equals C, the protocol accepts with probability 1. In case 2, GS A1 A to AS, the protocol not being C, the protocol accepts with probability at most epsilon m, and this epsilon m happens to be md over the size of the field where m, what was m? M is this quantity. The number of operators. This is each of the operators, whether the existential, operational, existential, universal, or the linearizing, the number of such operators. So there are n square of them. M itself is now like n square. All I want to claim is this is true. And we can do the proof of it, but I don't think the proof of it is any more insightful than the other proof. It's just a cumbersome calculation. If you want, you can look at it and we can discuss it all the office hours if you want. I just want to skip this proof. This is the idea. The only idea was linearization to get back efficiency, and then it's the same proof as we did for sharp set. But let's pause, some questions, and then go on to the next.
So what was this claim about?
This claim says that at every, it's similar to this claim, a claim which which we proved in the previous thing, but we did not explicitly write. So in the proof of the permanent, what did I say? In the proof of the previous thing, we said we will give an IP protocol for anything of this form. An intermediate, this is an intermediate step in the protocol. That is, you will reduce to this.
Oh, so this SI is sort of the G here.
The SI is the sort of the G here. Yeah.
Okay.
For an intermediate step, we have this. That's all I'm claiming. Okay. This proof is no more insightful. That's one reason why I'll skip the proof. It will take me 15-20 minutes to just write down the proof. Skip the proof. The only thing that's happening, the only key difference between the sharp-sat proof and the TQBF proof is the degree reduction. If you didn't do degree, the degrees just blow up arbitrarily, and you just make this observation that you only care about it at Boolean places. Therefore, each time you can linearize the degree. You can get the degree back to 1 by applying this linearizing operator, and hence you start off with a control degree, make the entire polynomial multilinear by linearizing operator. You do one of the existential or for all operators, that is going to potentially double the degree. Once again, apply all the linearizing operators to make it back multilinear, and keep doing this. Each time you do an operation which blows up the degree by a factor of 2, you apply all the linearizing operators to get the degrees back in control and keep doing it. That's all. So all this has a change is the number of rounds of protocol, instead of being previously linear in the number of rounds, it's going to be polynomial in the number of rounds. That's all. It's going to be quadratic now.
So at the end, you had an n-variate degree 2n polynomial, right?
Yes. No. At the end, actually, there is no variate. Each variable gets eliminated. It's a large constant.
It's a constant. Oh, sorry. Yeah.
Constant. It's just that you want to check that that constant is 1. Its constant is written in a horrible fashion. It's written as something plus something.
No. You need to send the px, right?
No.
The px.
Px is before the last thing is a constant. You need to check after shaving off the previous guy. It's not a constant. It's a univariate polynomial. That univariate polynomial, when you evaluate it at 0 and 1, the product happens to be the constant. Is what you want to show. If the quantifier was for all.
So what does the prover send back to the verifier in the first case? In the first step, what does he send back?
That is similar to this. The first step, what he sends back is, so he has to set p psi. P psi is a constant, but p psi itself is p phi of 0 times p phi of 1. It is this.
The prover in the first step sends p1 x1, right?
Yeah, which is what? Which is the.
Now, if it's a degree n polynomial with in
Let's look at it. Let's psi is for all x1 some nonsense over here, which is fully quantified in all the remaining variables. This was p. What the prover is going to give me is the polynomial p phi of x1, because that's what the prover is going to give me. It's this univariate polynomial in the x1. To show to me p phi is 1, he is going to give me p phi of x1.
Oh yeah.
You will need to stare at this a little longer to get comfortable. That is, it will seem as if the variables are increasing, but the variables are, as the protocol is going, is also decreasing. Eventually, p phi is just one horrible way of writing a constant, and I want to check that that horrible way of writing a constant is actually 1. That constant.
What I was confused in is, like, suppose you want to, even if you want to say under degree n polynomial, degree n variate a degree n polynomial, which is sort of a polynomial in n variables that has like n plus n choose n monomials, right? That would be too big to write down, is what I was worried about.
Notice at no point of time we send a multivariate polynomial. Always the prover is sending only univariate polynomials.
Univariate polynomials, yeah.
Univariate polynomials. So only so for a univariate polynomial, the number of field elements is just the degree. It's not just choose things doesn't come into the picture.
Yeah, the choose thing.
Okay. So what I will do next in the remaining about 10 minutes that I have is an outline of what we are going to do in the remaining 2 lectures in interactive proofs. Why do I do all of this? So let's make some observations in the proofs that we have seen so far. So what have we seen so far? So far, IP, it's a new model of proof verification. We defined this model. Then the toy example, we gave a protocol for graph non-isomorphism. Give an IP protocol. And it was crucial that this was a private coins protocol. That is the randomness which the verifier took. He did not reveal the randomness to the prover. If the verifier revealed this randomness, the whole soundness would have been destroyed. But then we also went and gave ahead for P space or permanent or whichever, sharp P, one of these, all these protocols. We gave an IP protocol for this.
These were public ones, right?
This was completely public coins. The verifier was not doing anything. except at the very last step, he makes a verification. He just keeps tossing random points and keeps sending it across. All the checks, we actually set it the intermediate step, but all the checks could have also been pushed all the way to the end. So till the end of the protocol, the verifier doesn't do anything. It just tosses coins, tosses coins. And these are very specific things called Arthur and Merlin proof systems, in which public coins, in which Merlin is this all-powerful wizard who's doing all the computation. Arthur is this weak king who all he does is keeps tossing random coins and sending across to the proof to Merlin. And so these are called Arthur-Merlin proof systems, in which there's this all-powerful being who's doing all sorts of computation. The verifier is so weak, it's not even doing any computation. It just tosses random points at every single step. And we actually showed that even if such a weak verifier, the verifier doesn't do anything, except at the very end, it does some computation. It makes a whole bunch of checks. Even such a verifier, just because this verifier is able to interact with this all-powerful prover, such a verifier can be convinced of any membership of any language in P-space. Okay. So these guys, I'm going to give a special name for it, public coins interactive proofs. So Arthur is the verifier here. Merlin is the prover. Proof systems. These are also called proof systems. And the acronyms Arthur and Merlin, it's A and M. The reason they come is, what is Merlin trying to do? Merlin is trying to maximize the probability of acceptance. It's a prover he wants. So Merlin is a maximize. His strategy is to find the best strategy. Arthur is a random coins. Therefore, he's not doing anything. He's just finding an average strategy. So Arthur stands for, A stands for averaging, M stands for maximizing. It also stands for Arthur and Merlin. This is in one case, sort of these, you're playing this game in which one guy is just tossing random coins, the other guy is actually doing all the clever computation, and even then you can actually show that this game is actually an interesting game. You can prove problems in P-space.
So all these
yeah.
permanent and for permanent and sharpsat, these were like AM poly, right?
AM poly, exactly. So this is the language I'm going to define. Yeah. So L has a public coins IP protocol with utmost KN rounds. If I define this AMKN to be this, and similarly IPKN is the same thing, in which potentially private coins. What have we shown? We have shown graph non-isomorphism is in IP2, but we have shown that P-space is in AM poly, which by definition is also in IP poly. A public coins protocol is a special case of a general protocol. Okay. So given this, I'm going to list out a bunch of properties of AMK and IPK, some of which we have seen already. The first is what we have seen so far. We have seen that P-space is contained in AM poly.
Because of the TQBF thing, right?
Huh?
Because of this TQBF thing, right?
Because of the TQBF thing. IP poly, and IP poly is in P-space. So this sequence which we did, we already did in class. Over the last 2 lectures, this is what we did. We didn't do fully that P-space is in AM poly. I gave the hint that the proof is similar to this one. The next thing which we will observe is a very surprising thing. We'll show that take any IP protocol with kn rounds. This is potentially a private coins protocol. This is actually contained in Amk and +2. So if you allow the protocol to just increase by one more round, two more rounds, I can just collapse it down to a public coins protocol.
So also like property one also gives you this, right? Like not this.
No, property one proper. This let's see. This is public coins versus private coins. Let's see whether it say. So one corollary of this fact. Sorry, this is it's not 2, it is 1. With just one extra round. One corollary of this fact is graph non-isomorphism, which was in, sorry, this was also IP1, which was in IP1, is contained in AM2 because of this. Just to verifier sending a message, prover back, verifier message. With just this, you can do it. AM2 is author sends a message, Merlin returns, author sends a message, Merlin returns. Notice that this corollary I cannot get by the previous thing. Previous thing will say graph non-isomorphism is in AM poly. Because graph non-isomorphism is reducible to TQBF, TQBF is in AM poly. It will not give you a 4-message protocol that solves this one. Okay. So this is something which we'll prove in the next lecture. Another thing which is a nice concept is for all constant scale. For all constant scale, AMK is actually contained in AM1. So if it's a constant round public coins protocol, all you need is author and Merlin, just one round of back and forth.
Just sort of ask all the questions in a single like.
It's not. The proof is far more involved. The proof is far more involved than this. The corollary of this is the fact that graph, if you put it with the previous guys, that graph non-isomorphism is in AM1. And AM1 is just called AM, by the way. Okay. Ram Prasad, you seem quite troubled. Or you are. Huh? Okay, you're muted.
I was doing something else.
Okay, fair enough. Okay.
So, what if in a protocol some coins are revealed and some coins are kept private?
So that's a private. This one, even that one, any protocol, not necessarily a private coins protocol. I claim it. I can make it into a public coins protocol with just adding one more round of interaction. I can just make all the coins to be public. I'm just telling an outline of what we are going to do. AMKN, this is something which we said we can assume without loss of generality, it has perfect completeness. So recall once again, 1, we already did it. 2, we will do it in class next lecture. 3 and 4 will be going into problem set 5. Going into problem set 5. Okay, why am I doing all of this? So these seem just like definitional things about various things. You'll see that once we have these 4 properties, next lecture will show, given just these 4 things, we can now ask graph isomorphism. This is one of the problems in NP for which we haven't been able to show it's NP complete. But we haven't even been able to put it in P. It's a problem which is sitting in the netherworlds. It's neither in P nor is it NP complete. It's one of those intermediate problems. So question asked is it NP complete? We will show that all these 4 properties which I listed above will show you that actually if graph isomorphism were NP complete, the hierarchy will collapse. So there's a reason why we have not been able to prove graph. We were not be able to reduce SAT to graph isomorphism, because if we had reduced graph SAT to graph isomorphism, the hierarchy would have collapsed to the third level. Notice that this is a statement which has nothing to do with the interactive proofs. It's asking, is it possible to come up with, show that graph isomorphism is NP complete? I will just use the 4 properties I listed right now to show that these 4, given that these 4, we'll prove these 4 properties over the next few lectures and your problem set and stuff. But given these, we will show that it's unlikely graph isomorphism can be NP complete. If graph isomorphism is NP complete, the hierarchy will collapse. And this, I think, is an extreme success of this theory. It's an interactive proof. It's a fantasy of, it's a figment of our fantasy. We came up with this in which you could talk with this prover. Who knows if such a prover exists and all? But yet we are out of this. We are able to prove this one line which shows that graph isomorphism is not NP complete, because otherwise the hierarchy will collapse. This is a statement which has nothing to do with interactive proofs, but we'll be able to prove this just with the 4 properties I mentioned. And that's why these 4 properties are useful. These are not just some arbitrary properties of these interactive proof protocol systems. It is actually, it tells you something about graph isomorphism and graph non-isomorphism. And we'll start off next lecture by showing that these 4 properties will imply the unlikeliness of graph isomorphism being NP complete. And then we'll go into the proofs of some of these properties over the next lecture. Yeah, I will stop with this. Any questions? Hopefully problem set 4 will be out by the end of the day. Problem set 4, problem set 3.
4.
Four.
I given 4 problem sets already.